So the story that we're going to cover now is basically a summary of what we've already talked about. We're going to be talking about two states and of human metabolism, and I want you to focus on the terms like glycogenesis, glycogenolysis, glycolysis, gluconeogenesis, and so on and so forth. Clear? So the first state is absorptive state. Absorptive state is the one after each meal. So now think what happens when you eat, food gets digested and nutrients enter the blood. Abundant nutrients are absorbed into the cells where they are used for synthesis or anabolism of biological macromolecules. Protein is going to be synthesized from amino acids. Glycogen will be synthesized from glucose. Glycerol and fatty acids, wherever they come from, will be used to synthesize triglycerides. During absorptive state, after the meal, all the monosaccharides, galactose, fructose, will be converted into glucose in the liver. And glucose subsequently will be used as the major fuel. It will be the main source of energy for your cells in absorptive state. As we just discussed, excessive glucose, the one that cannot be used as the source of energy, where is it going to be stored first? Glycogen. And when glycogen storage is overwhelmed, fats. Does that make sense? Now, you have, when we say glucose as the energy source, fat as the energy source, you have to appreciate that all these cells are going to use both glucose and lipids, triglycerides, as the energy source. Am I clear? They're going to be using both. But organs like fat, adipose tissue, liver, and muscle will be using mainly lipids. And the rest of the body will be using glucose as the energy source. Does that make sense? Now, excessive lipids will go into this storage in adipose tissue. Excessive glucose will be converted into triglycerides eventually and will be stored. Does that make sense? Now, what happens to amino acids that are derived from the protein? Some amino acids will be used as the energy source. That's inevitable. Some after deamination, transamination. Some of them will be converted into triglycerides. You with me? This is what we just discussed, high glucose, high everything. But the majority of amino acids will be used by the cells of the body for the protein synthesis. So this is absorptive state, right? And this, I'm going to wrap up the talk and I'm going to ask you if you have any questions. So this is your GI tract. Glucose gets absorbed, used as the energy source by all tissues. Triglycerides stored in the adipose tissue. Glucose is also converted into glycogen in the skeletal muscle. When glucose is reaching adipose tissue, it will be used in the process of lipogenesis to produce triglycerides. Does that make sense? In the liver, glucose will be stored in the form of glycogen. And it will produce triglycerides as well. Now, amino acids will be mainly utilized for the protein synthesis. Now, any questions? I'm getting there. So, glucose in the absorptive state, what is it going to be used for? Tell me. Energy. That's glycolysis. And here's the deal. We're going to name the processes that are going to be increased, right? So if glucose is used for energy, glycolysis is up. What else glucose is going to be used for? Synthesis of glycogen. Glycogenesis is up. Excessive glucose will be used for synthesis of triglycerides. Lipogenesis is up. Does that make sense? Now, well, we'll get to the hormonal regulation. Fat. In the absorptive state, fat, where does it go? In a fat tissue, yeah, in adipocytes, right? Amino acids. What are they going to be used mostly in the absorptive state? Protein synthesis. So protein synthesis is up. Does that make sense? It doesn't mean that some of those triglycerides or protein amino acids will not be used for energy. But the majority of triglycerides will be stored if glucose is abundant, and the majority of amino acids will be used for protein synthesis. Am I clear? I'm talking about the situation when you have a lot of everything. A lot of glucose, a lot of amino acids, a lot of triglycerides. We good? Glycogen, where is it synthesized the most? Which two tissues? Skeletal muscle and liver. Yes. Those are main glycogen storage facilities. Which hormone will regulate absorptive state? Which hormone is produced after the meal? Insulin. So insulin will increase amino acid uptake into the cells. And just think about it from the common sense standpoint. Insulin increases uptake of amino acids. A lot of amino acids will be used for protein synthesis. Just perfect, right? Glucose goes into the cells. In the cells will be stored as a glycogen or stored as a fat or used in the process of energy generation. Does that make sense? So this, look, let's decipher what's going on. So when you have all those nutrients in the blood, insulin will increase glucose uptake. Does that make sense? It will increase amino acid uptake. Insulin, what will it do to glycolysis? Now you're going to be using only two words, increase or decrease. Insulin, how will it change glycolysis? Come on. Increase, look. Insulin allows cells to take glucose in, right? It's not just for the sake of taking it in. It's for the sake of doing something with that glucose. What can you do with the glucose inside the cell? Tell me. 3 things. Break it down. Ooh, slow down. Break it down. How do we call this process? Glycolysis. Okay. So insulin will increase glycolysis. What else can we do? Store it in the form of Glycogen. So glycogenesis will go up. Or we can store it sort of in the form of what? Fat. Lipogenesis will go up. And finally, protein synthesis will go up because amino acids are taken into the cells as well. What about glycogenolysis? It's inhibited, right? Glycogenolysis, it's inhibited. You don't need to break down glycogen. You're storing it. What about lipolysis, breakdown of fat during this process? It's going to be down, of course, because you're storing fat. It's counterintuitive to break it down. Does that make sense? So basically, if you will start just, like eating and shooting yourself with insulin, you're going to become really muscular and probably really fat as well. Glycogenolysis, breakdown of glycogen, is inhibited. Right? Lipolysis is inhibited, breakdown of fat. And obviously, synthesis of glucose, gluconeogenesis, is inhibited as well. Good? So, insulin is called hypoglycemic hormone because it decreases the blood glucose. Now, post-absorptive state. Look, opposite. So, this happens when you're hungry. What happens to your blood glucose when you're hungry? Does it keep falling? Huh? Your blood glucose? No, it doesn't keep falling. Is it steady when you're hungry? Yeah. Because what? Which organ needs glucose? Speak up. Brain. Exactly. So you have to maintain a steady blood glucose because of the brain requirements. Does that make sense? Which hormone maintains your blood glucose steady when you're hungry? G-word. Huh? No, ghrelin tells you I'm hungry. Ghrelin is the hunger hormone. You're absolutely right. But which hormone regulates the release of glucose into the blood? Huh? Insulin is from the blood into tissues. The opposite of insulin. The G word. Opposite of insulin. Alpha cells produce it. Insulin is produced by beta cells. Alpha cells produce glucagon. There you go, glucagon. Okay? Now, what happens when you're hungry and you're not eating? Proteins broken down into amino acids. Glycogen is broken down to release glucose. Triglycerides, your fat, is broken down to produce glycerol and fatty acids. Does that make sense? Now, glucose, fatty acids, and ketones will all be used as a source of energy. Does that make sense? Now, gluconeogenesis will occur mainly in the liver, where amino acids will be converted into glucose. So you have two sources of glucose in the post-absorptive state. One is glycogenolysis, right? And another source of glucose is gluconeogenesis. Glycogenolysis is the breakdown of glycogen. Gluconeogenesis is what I was about to say. Generation of glucose from scratch. Does that make sense? Now let's see. You're hungry. You're not eating anything. You keep starving. What happens to your glycogen storage? Yeah, decreases. It's basically depleted. What goes next? You're still starving. What goes next? Huh? Both muscles and fat. okay? Because you will need fat as the energy source here, fatty acids and ketones, right? And you will need muscle protein for gluconeogenesis. Am I clear? That makes sense. So this is why if you try to lose weight, like hardcore lose weight, it's really hard to build muscle mass at the same time. Because you probably going to be using some of those muscle proteins as the source of glucose. Does that make sense? Especially if you go into low carb diet. Okay? Now, glucose sparing. That's what Marina and I were talking about during the break. So in some cases, in many cases, when you starve long enough, the metabolic shift occurs in virtually all cells in the body. And they start to use ketones as the main energy source, leaving more glucose for the brain. If you are in ketotic state long enough, brain adapts to it, shifting its metabolism towards utilizing ketone bodies. Does that make sense? Now, a quick, sort of, not digression, just a commentary here. You have to understand that we don't have tiny little people sitting in our cells, just, switching triggers. Instead, when, the body milieu changes, like, your extracellular fluid changes, pH, organics concentration, like glucose concentration, ketones concentration. This is sensed by chemoreceptors, and that triggers certain signaling in the cell, which will lead to shift in gene expression, for instance, or activity of the proteins. Does that make sense? This is all chemically regulated processes. You good? So this is basically the scheme that is opposite to what we saw for absorptive state. So you're starving. Triglycerides from the adipose tissue will be broken down to glycerol and fatty acids. So fatty acids can be converted to keto acids. And ketones, or keto acids, can be either used as the energy source or be converted to the ketone bodies, also used as the energy source. Glycerol. Remember we talked about what happens to the glycerol in the context of glycolysis? Glycerol can be converted to G3P, right? And G3P can be converted back into the glucose. There you go, you have glucose that brain requires. Okay? Now that glucose will enter the blood to fuel the brain. And that glucose will come not only from the catabolism of lipids, it will come from the glycogen and from the keto acids, the products of the protein catabolism. Does that make sense to you? So we have all the processes that are opposite to what we see in absorptive state. Now, this is the feedback pathway on the left. So you have low blood glucose, which stimulates the glucagon release. Now, glucagon will stimulate glycogenolysis. What is glycogenolysis? Can you tell me? Not creating. Glycogenolysis. Well, creating of glucose. But what is broken down in glycogenolysis? Bless you. Glycogen, yeah. Glycogenolysis is breakdown of glycogen. And gluconeogenesis. Gluconeogenesis is making glucose from scratch. So that happens in the liver. Glycogenolysis and gluconeogenesis mainly happens in the liver. That make sense? Now, in adipose tissue, glucagon will stimulate lipolysis, breakdown of what? Fat. Yep. Which increases free fatty acids and ketone bodies. Does that make sense? Does that make sense to you? Now, you know what's interesting? Look at this. Look at the effects. So liver will start releasing glucose in the blood. Okay. Adipose tissue will increase plasma fatty acids, which will spare glucose, further increasing glucose levels in the blood. So glucagon, indirectly, will increase the insulin production. That's your example of teeter-totter. When your glucose increases in the blood, insulin increases as well. Does that make sense to you? Okay. Now imagine that you take high protein, low carb milk. Low carb, elevated glucagon. Elevated glucagon, elevated blood glucose. Elevated blood glucose, elevated insulin. Elevated insulin, elevated amino acid uptake. So, what does that mean? If you eat high protein, low carbohydrate meal after the workout, you will increase the uptake of amino acids tremendously into the muscle cells, and you will stimulate the protein synthesis into muscle cells. So this is the physiological basis under the idea that after the workout, you have protein shake. Does that make sense? You don't do it before workout, you do it after the workout. Because this is when hormonal levels, glucagon and insulin, are optimal for proper regulation of blood glucose and uptake of blood amino acids. Yes?
So if you're trying to gain weight, would you take the protein shake after still?
If you try to gain muscle weight or just weight. If you try to gain weight, I don't know why, but just eat whatever you want. Okay. That's seafood diet, I know. What you see, that's what you eat. Yeah. But in general, specifically for muscle gain, it actually exemplifies that you need not only protein, you need certain levels of hormones to facilitate the proper amino acid uptake. If you just try to gain weight, then I'm really jealous. I'm really jealous. Now, and that kind of repercusses with the idea about anabolic and catabolic hormones. So anabolic hormones are the ones that facilitate the synthesis of the proteins, for instance. So first, look at insulin. Okay? Look what it does. Oh, before we move on, let's quickly review which processes are up in the post-absorptive state. So in the post-absorptive state, glucose, what is it used for mainly? Which organ is it directed to? Huh? Brain. It is directed to the brain. So in all other cells, glucose breakdown is increased or decreased? In all other cells except brain, glucose breakdown should be decreased, so there's more glucose for the brain. Does that make sense? So we can say that glycolysis is down. What about glycogenesis? Making glycogen. That's down too. What's up? Glycogenolysis is up. Okay? Now, how do we get glucose from scratch? What's the process? Gluconeogenesis, and it is up. Now what about fat? When you're starving, are you going to be storing fat? No. So lipogenesis is down, and lipolysis, breakdown of fat, is up. Okay? What about protein synthesis versus protein catabolism? In starving state, post-absorptive state. Protein synthesis should be down because we may need proteins, amino acids, for glucose synthesis. So protein breakdown will be up. Does that make sense? There will be 2 or 3 questions on the exam. And I give you examples of what it's going to look like on the quiz that you're going to collect today. Where, like, which processes are upregulated in the post-absorptive state? Which processes are downregulated in the post-absorptive state?
So, lipogenesis is
Making fat.
So that's down, right?
In this situation?
Yeah.
Absolutely, yeah. You're not storing any fat. You're using it, actually.
So in the opposite of that, so lipolysis is up.
Absolutely. You're absolutely right. Yes, lipolysis is up. Now, hormonal regulation. I want you to focus on this 4. Okay? So, blue are anabolic. Insulin increases uptake of glucose and amino acids. Increases glucose breakdown, storage of glycogen, storage of lipids, and it actually stimulates protein synthesis. Okay. Growth hormone, same. Thyroxine stimulates protein synthesis. And testosterone stimulates protein synthesis. Does that make sense? So you have 4 anabolic hormones: insulin, growth hormone, thyroid hormone, and testosterone. In terms of the stimulation of protein synthesis, testosterone is the most powerful, the most potent. So professional bodybuilders, they're not only having a very special diets with a very well calculated amounts of proteins and lipids and fats and sugars, they also usually, they're not using testosterone now at all. They use derivatives, okay, that are safer on the liver, for instance. But they will not use just those derivatives. They have very well calculated hormonal treatments that include testosterone derivatives, insulin, growth hormone, and in some cases thyroid hormone to get rid of the extra fat storage. Does that make sense? So I'm not telling you, go and do it, but just give you an idea that it's not just shooting steroids. It's way more complicated than that. Am I clear? Because, say, thyroxine will allow you to get rid of some fat, and the growth hormone as well. Does that make sense? You understand what I'm trying to say? Now, the catabolic hormone that I want you to focus on, cortisol. The stress hormone actually stimulates protein breakdown. It stimulates fat breakdown as well. Catabolic, anabolic, we apply it in relation to protein metabolism. So basically, in order to gain muscle mass and lose fat, you have to somehow do things that are absolutely opposite. You have to lower your BMR to increase thyroid hormone synthesis. You have to somehow increase your growth hormone synthesis. You have to somehow increase your testosterone. You have to increase your insulin. And at the same time, on top of that, you must not be stressed. So you produce very little levels of corticosteroids. Does that make sense? So again, insulin, growth hormone, testosterone, and thyroid are anabolic. Cortisol is catabolic. We clear? So the only thing that I'm going to ask you here about really, which one of these 5 is catabolic, which one is anabolic. So all you need to remember is that cortisol is catabolic because the rest of them are going to be anabolic. Okay, we're good? That's pretty straightforward. I'm not going to ask anything beyond this 5, I promise. Food intake regulation. This is way more that I want to address. But I want just to show you some interesting, intricate links between hormones and food intake regulation. So first of all, food intake is regulated by hypothalamus. Okay, you have so-called arcuate nucleus in hypothalamus, which controls your food intake. Does that make sense? Now look at the left of this picture. This part. Stretch or distension of alimentary canals. Stretch or distension of stomach or intestine. It gives you a signal that what is present there? Food. Glucose, amino acids, fatty acids. Where are they coming from? Food. What are the stimuli for insulin or cholecystokinin production? Food. So when you have food in the system, either by gut hormones or chemical signals from nutrients or nervous signals by vagus nerve, all of that leads to the stimulation of a specific part of the arcuate nucleus, which gives you a sense of satiety. Does that make sense to you? Here's like all these signals: insulin, CCK, distension, presence of nutrients in the blood. They are all associated with already eating. Am I clear? That makes sense? Cool. Now, what will give you hunger? Well, glucagon is associated with not eating, fasting, right? Blood glucose drops, fasting. Ghrelin is just a hormone of empty stomach. Finally, interesting thing, epinephrine. That's really cool. So let's remember about epinephrine. So epinephrine, okay. Glucagon and ghrelin will directly stimulate neuropeptide Y and agouti-related peptide-releasing neurons. What hides behind those fancy words? It's a hunger part of arcuate nucleus. And you're going to feel hunger. Now think about it for a second. Let's say you had breakfast, okay? And then for the entire day you were working at the desk. You didn't get anything, just drink some water. Are you going to feel hungry? Well, the entire day. Like you had breakfast at 6 a.m. at 6 p.m. now. Probably, yeah. You probably should, right? That's normal. Now, you had breakfast, and a couple of hours later, you went on a good run, like 4 miles run. You come back. Or you had a really good walk with friends, some kind of exercise, which leads to the release of which hormone? Epinephrine. That makes sense? And what you're going to do? You're going to eat because you're hungry. It was shown multiple times that exercise, paradoxically, without diet, leads to the weight gain. Because when you exercise, you feel hungry, you start consuming food, without physiological justification to consume it. Does that make sense? You don't really need it. You feel hungry because you exercise, because of that positive stress. Does that make sense to you? I think it's just kind of cool, you know, that you feel hungry just because you had that sympathetic activation. It's the result of exercise or just walk. Make sense? Of course, leptin inhibits your appetite. Insulin can inhibit appetite too. So you have to kind of have an idea that, you know, if you have a food-associated signal, it will inhibit your appetite, right? If you have hunger-associated signal, it will stimulate your appetite. And damage to hypothalamus, by the way, can lead either to chronic wasting, people just don't want to eat, or hyperphagia, when people feel hungry all the time and just keep eating. Does that make sense? Now, BMR. I found this table of how to calculate BMR. If you want, when you're free, you can play with those formulas. Okay? I don't have my cell with me, so that's for like different ages, 18 to 30 years. I'm out of the range, so not applicable to me. This looks like a really, really long one. The simple way to estimate your BMR. If you're a man, 1 kilocalorie per kilogram per hour. Okay, so say I weigh about 80 kilograms. Okay, so I spend about 80 kilocalories an hour. There are 24 hours in the day, so I'm going to be spending 1,920 calories a day if I lay flat without moving. Does that make sense? That's BMR. You understand what I'm saying? You're not moving, you're not doing anything. BMR measures how much energy you spend for your like absolutely fundamental metabolic functions. Is that understood? In women, BMR is slightly lower because they have higher percentage of fat normally. Okay? Is that understood? You will not need to calculate the BMR. Okay? But I do want you to understand what increases basal metabolic rate, what decreases. We'll get to this. Now, regulation of the body temperature. Well, when we cold, what do we do? We shiver, that's a skeletal muscle, it produces energy, right? When we hot, what we do? We sweat, we also dissipate energy directly, and we get all red, so the blood flows to the superficial, to the skin to dissipate heat, right? When we cold, we pale because blood vessels constrict to contain energy. We have two temperatures. We have core temperature and shell temperature, right? So shell temperature is the temperature on the surface. It can be as low as 22 degrees Celsius and you're still fine. Core temperature is pretty standard. It's about 37. Okay. Normal range is shown here. So you can have the temperature of 38.2 Celsius, which is something like 101. I don't remember exactly in Fahrenheit. And you're still not sick. Is that understood? Anything out of this range is abnormal. Now, people can survive in a pretty wide range of temperatures, body temperatures. So probable survivable maximum is 43. Realistically speaking, there were cases of people who were hospitalized at the body temperature, measured body temperature of 46 degrees Celsius. It is a lot. Like, really a lot. We're talking 4, 6 Celsius, like 116 Fahrenheit. That's a lot. They survived. Okay, they were cooled down. Eventually, temperature was brought down. They survived. Okay. Now, what about lowering the body temperature? You know about cooling people during the cardiac surgery to lower the metabolism and minimize the risk to the brain. I don't remember if I mentioned it for you, but people were recovered without any apparent brain damage from the core body temperature of 22 degrees Celsius. That is really low. We're talking like 72 Fahrenheit body temperature. Okay? That happens, especially in the northern United States, that happens every so often. People are collected on the streets, like some remote areas where they froze. Okay, and they can be brought back to life. What I wanted to say. Oh, measuring body temperature. All our thermometers are very unreliable. Because what temperature are we measuring? Core or shell? Shell or something in between. If you do this under the armpit, that's shell. It's not reliable. You stick into the mouth or up into the rectum, better, but still not. There is a way to measure core temperature. It's pretty brutal. The thermometer is swallowed. It's like a little tiny wire, a little tiny kind of tablet. So you swallow it, you can measure core temperature. I mean, nobody's going to do it. It's just, we don't need that parameter, at this level of precision. Does that make sense? So the temperature that we measure is pretty okay. All right? Now, what can affect basal metabolic rate? So I found this paper's age, obesity, being female. Let's work our way through these images. So on the left, you can see the distribution of the basal metabolic rate in the study group. Men versus, so that's based on age, okay? Do you see that? So here is the group 18-19. This is the group 19 plus. You can see that basal metabolic rate decreases. Does that make sense? Now, this is just one study that I found. Okay? It is a very well-known phenomenon. With age, your BMR goes down. Now, what does that mean for you in your real life? Your BMR goes down means that you burn less calories when you do nothing. Does that make sense? Now, it becomes a reality. When you are 18, 19, 20, you eat whatever you want, you don't gain weight. You keep that same level of activity, same level of food intake, you start gaining weight as you become older because your BMR decreases and you're not burning as much energy. Does that make sense? Sorry. In the large-scale studies, generally speaking, BMR starts to drop after 30. It never comes back. It just keeps dropping. Okay? Obesity. Elevated body mass index is strongly associated with decreased BMR. Does that make sense? So people, and that makes perfect sense because people who are bigger in size, they usually have more adipose tissue. Adipose tissue is very metabolically inactive. So that is what decreases, okay? So age decreases BMR. Female sex decreases BMR. Obesity decreases BMR. What increases? Stress. thyroid hormone, oxygen consumption. So your BMR increases if you breathe more frequently. Elevated body temperature increases BMR. Increased muscle mass, well, muscles are more metabolically active. And increased food intake, alcohol included. Okay, so when you drink a lot and eat not a lot, you may actually drop some weight. That happens. Okay, I've witnessed it. Now, this is a really interesting story. So that was the study that was looking at the RMR, refers to resting metabolic rate, and I want you to focus your attention on that particular part. So RT refers to a group that underwent just resistance training. C is control. RT/W is the group that underwent resistance training and endurance exercise, okay? Walking, aerobic walking. Well, it turns out, it seems because it's not like millions of people, but it seems that, first of all, resistance training increases BMR. Okay? So, if you compare after exercise with before, does that make sense? And it increases compared to control. Well, resistance training with walking afterwards decrease BMR. So if you do resistance training and then do some aerobic activity, that will actually lead to lower basal metabolic rate.
So is that saying like that cool down period that they say is BS?
Yeah. Stretch is fine, but cool down is BS. So actually empirical evidence suggests that to achieve best results in aerobic activity, so first of all, if you do it for like your own health, okay, just to stay physically active, basically, you have to combine, you should combine resistance training and aerobic training, right? That's known. But empirical evidence suggests that you should not combine these two together. So if in the morning you jog, just jog. Go to the gym in the evening. And vice versa. Does that make sense? Try to split these activities. Yes?
So you should like run on the treadmill and then go lift after.
Like, go lifting, enjoy your day. In the evening, do the treadmill, do the jog, whatever, walk.
All in one.
Don't try to cram all in one. Again, exercising is good. It's great just by itself. It's awesome, okay? But once in a while, it's not a problem. But if you develop a long-term program for yourself, split those two. Split resistance and endurance. Okay? Now, in the long-term perspective, resistance training increases BMR. Just in the long term, like real long term. Okay? Now, that's the last thing to talk about. How do we regulate body temperature? I'm going to break it down much simpler than all this text. First, how do we know that it's cold? No, that's not how we know. Huh? We have receptors, right? We have sensory receptors. That's how we know that it's cold. Signal that it's cold goes to hypothalamus. The hypothalamus is your thermostat. Does that make sense? So if it's cold, what's going to be the output? Shiver, okay? So you're going to start shivering. What's going to happen to the blood vessels, peripheral blood vessels? They will constrict. if it's really, really, really cold, and those blood vessels stay constricted for a really, really long time, what's going to happen to the tissues in your, like, fingers, huh? They're going to become necrotic, hypoxia, right? The frostbite. Does that make sense? But it'll save the energy for the core. So you're going to be shivering, going to be all pale, but your core temperature will remain the same. Does that make sense? Now, what if it's really hot? Sweat and blood vessels in the skin will dilate, dissipating the heat. Does that make sense to you? Actually, cooling down increases BMR. It was shown that mice, if you put mice in the constantly cold conditions, the basal metabolic rate will increase and they will lose weight more efficiently. Okay, I'm not suggesting, get naked and start running outside in Minnesota, but that will increase BMR. All right. Now, a few things. Why people get heat stroke? When people get hyperthermic, so say they are running in Houston in the noon, in the summer. People get hyperthermic. They don't have enough capacity to dissipate all the heat. That hyperthermia depresses the activity of hypothalamus. So basically somebody just switches off the thermostat. Does that make sense? So hypothalamus stops sending signals to sweat and be flushed to peripheral tissues. Am I clear so far? You keep running, your temperature climbs up, your BMR increases, your temperature climbs up, your BMR increases, your temperature climbs up. How do we call this type of feedback? It's positive feedback. So eventually when temperature reaches a certain level, organs start to fail. Enzymes start, to get denatured, all that kind of crap. That makes sense? So in a heat stroke, you cool people down. People usually will lose consciousness. Okay? You have to administer fluids usually because they lose a lot of fluids with sweat initially. So, it's pretty, yes.
I knew this kid, he was at football practice during summer.
Yep, in Kent?
Yeah.
Kent State University. Yep, a couple of years ago.
Oh, well, this back was hard, but he passed out and ended up having heat stroke.
Yep, dehydration and loss of blood flow to the brain. Okay, there's as far as I remember, a lack of proper cerebral blood flow regulation. And that's it. That's pretty common.
So was that due to not drinking enough water?
That is due to the coaches being morons. Because when you see the first signs of the heat stroke, you're not trying to take care of it yourself. You're calling 911. In the meantime, applying cold and trying to get some fluids into the person. Right away. And generally, just don't do that. Just don't run them to death. Okay, that happened 2 years ago at Kent State. They ran a kid to death. Okay. In hypothermia, so your vital signs decrease, and that also depresses the activity of hypothalamus. So heat generation decreases, you keep cooling down. Heat generation decreases, you keep cooling down. People who were recovered from hypothermia, who were almost dead, said that it's the most comfortable way of dying. Because your conscious perception shuts down before you die. Does that make sense? So you don't really feel anything. Now, one of the most fascinating things for me is fever. We're going to talk about fever and we'll be done. You have an infection. Either your own body or a microorganism. They release compounds that are called pyrogens. It can be your inflammatory molecules like prostacyclins, okay, or thromboxane A, or it can be chemicals that are released from, say, bacteria. These chemicals react with the receptors in hypothalamus, and they change settings in the thermostat. What is the normal setting in your thermostat? Tell me. It's written right here. What's the normal setting? 37. That's normal setting. It's a range, but 37. Does that make sense? The new setting is, say, 39. Now there is a mismatch. The setting is 39, but your temperature so far is 37. How can you increase your body temperature? What do you need to start doing? Huh? Oh, what? You're not going to be running around when you're infected. You're just going to start shivering, right? And then how do you store the warmth inside? How do you keep it inside in terms of the blood vessels? They constrict. So when you have fever, you shiver and you pale to keep all the warmth inside to elevate your body temperature. Yes? Not really. Not really. It's a side effect. So you have a fever. First of all, up until about 39 Celsius, generally, if there are no seizures, no vomiting, nothing abnormal except fever, you can just let it go. Because fever increases BMR, it increases healing, and it may also contribute to slowing down the growth of microorganisms. And it will limit the availability of iron in the blood, interestingly enough. Does that make sense? Iron is a necessary factor for bacterial growth. Fever is good. But let's say it's too high and you give, or there's some bad stuff is going on, and you give a drug like aspirin. Aspirin, ibuprofen, paracetamol, Tylenol, they will all counteract those pyrogens. Like ibuprofen and Tylenol, they mess with the synthesis of prostacyclins. Aspirin inhibits the synthesis of thromboxane A. Now, when you do this, those signals, they abruptly change. You quickly reset the thermostat from 39 back to 37. Now, your body is at 39, thermostat is at 37. How can you decrease your body temperature? Sweat. This is why you sweat when you get this antipyrogens. That makes sense? It's pretty. Okay, so